Awesome. So, thank you for having me here today. I'm Hank Roark. I work at H2O. I promise this is not actually an H2O talk. So, if you want to talk about H2O, we're here. So anyway, and to show that I actually do this for a living, I have no slides. I have an IPython notebook for today, which I somehow have to get into SlideShare. So real quick, a little bit about my background, and let me see if I can make this bigger now that we can see things on the screen. I have some things that screw up okay. So, yeah, I work at H2O. I've been there about 6 months. I'm still a part-time lecturer at the University of Illinois in systems thinking. I was previously at John Deere, where we dealt with a lot of sensor data coming off of machines. We combined it with stuff that came off of LiDAR data, airborne LiDAR, satellites, radar, all kinds of stuff. So I did a lot of work in geospatial and temporal data. I was at some startups, but maybe most exciting for me is that I'm back on the Georgia Tech campus. I can't believe I'm actually getting to talk on this campus after my academic record. So thank you to MLconf for inviting me. There's all my contact information. You can hunt me down. So this is I've ripped all of these images from somewhere. A good data scientist I reuse, but kind of the point is like, we're connecting more and more things. I mean, I worked at a company that was connecting, big pieces of metal that drove through, agricultural fields. There was a gentleman that was here. He actually had like 4 sensors on his arms today, so that was really incredible to see. We're basically instrumenting everything. So this whole IoT space is kind of taking off, and it's easy, like for me, to get biased in where all this can come from. So it can come from lots of different places. This is a great kind of graph of the different places the IoT data comes from. A lot of that is sensor data, so things that are measuring things out in the real world. The IoT is so hot, it's at the top of the hype curve for Gartner. I was just on Wednesday morning in San Francisco where Salesforce, Dreamforce was going on, where they announced their IoT cloud. So this is stuff that's happening. I thought working at H2O, we said maybe we should help them bring rain, but bring some water to it. So HP says this is going to be really big. The data that's going to come out of the IoT and sensors is going to be in this Brontobite scale thing. I have no idea what a Brontobite is. It seems really big. It's a lot of orders of magnitude bigger than the typical data sets, maybe terabytes on the big side that we're dealing with today. So how big is this? So they at least did provide us another graphic on how big a Brontobite is. So it's still not to scale, still little circles that aren't actually to scale. The ones that are out here to look at is that a zettabyte is how much data will travel on the internet next year approximately. So 1.3 zettabytes. A yottabyte is actually our digital universe today, or about what we think the U.S. government knows about people. So hopefully that places it in this kind of notion that sensor data is going to be really huge, and this IoT data kind of places it in scale. I was that previous place I was, they ran one experiment, and they collected, and this isn't much these days, but for them it's huge, a 30 terabyte data set in just a tiny little field experiment. So I mean, these data sets are going to get decent size, and across the world they will. So when you're dealing with this IoT sensor data, I think one of the things to keep in mind that it's not much different than any of the other data science we're doing. There's feedback loops, right? You go out, you monitor your environment, you instrument it, you monitor it, you do some analysis on it, you make decisions, and then you go control it. What's maybe a little bit different of what's going to happen, other than this data is going to be big, is that the decisions are going to be automated. They're going to actually affect things that affect people's safety and life, potentially, or health outcomes. So we kind of have a bunch of responsibility to figure out that whole loop. So there are people, for example, that I know, traditional engineering, when you're making a control system, you're modeling the physics of the system, you're modeling a control system, and that's how you're building up a control system. systems are getting so complex, I'm actually seeing people say, like, we actually don't know how to control the system. So what we're going to do is that we're going to go out and collect data of the system, and actually the machine learning is going to, the learn function is going to become the control function. And it's kind of going to be a little bit of a black box for us. And as long as it works, it's great. So it's some of the things that are a little bit different. Again, I do a lot of stuff. I care, maybe because of my background, kind of this industrial Internet of Things. So I needed, one of the big challenges, by the way, of working not at a company that has a lot of data, but at a software company, is you often don't have a lot of data. Your customers all have data. So I had to go out and hunt some data down, and luckily NASA was nice enough to provide this data set. So what they had is simulated turbofan jet engines. So think about the jet engine as you look out on your 737 or Airbus A320 type of data. And it was actually part of a competition for the Professional Society in Prognostics and Health Management in '08. And this is another pattern I see, right, is you're actually trying to detect and predict when this machine will no longer have any useful life, like when its remaining useful life has run out. So that's what prognostics is. Turbofan jet engines are kind of expensive, and they don't actually fail that often because people do a lot of maintenance on them. So you end up having to do a lot of physics-based simulations. And luckily, in this physics world, we have a lot of physics-based simulations that run in supercomputers, and even this one will run on a laptop if you can get a hold of it from NASA, which I haven't been able to do yet. Mostly because I can't figure out how to navigate NASA to get it done. So this is what the problem was. They give you 100 jet engines that have all, at some point in their life, had a failure interjected into them, and they degrade over time to 0 remaining useful life. So you get 100 of them. They're different lengths, so and they don't tell you why. They give you 23 sensors of data. You got 23, we don't tell you what they are, so you know none of the physics. So that was kind of the challenge, right? Can you turn data science on what is traditionally a physics problem? And then they give you another 100 that are run through some of their life, and there's like, predict how much longer until it's going to fail. So one of the things, and I love this, which is, this actually, the simple things work. So a lot of work that happens in the sensor data, and I've had to do before, includes things like these phase space embeddings where you're doing time delays, but then you have this problem with the curse of dimensionality. So this morning when Jennifer spoke with the EEG data, she got really great results on without having to do the phase space embedding. I found her over there in the crowd. So hi, yeah. So you didn't have to do the phase space embedding. It turns out sometimes that works actually really quite well. So you don't actually have to go through that step. So like of the lessons I've learned in dealing with this data is sometimes the simple things work. Just try them. Do what you do today, and they will often work. So I'm actually not going to run this notebook live in front of everybody because it takes about 3 hours. But one of the things so do simple things, do the stuff you do as data scientists. Here was, this is a sample of 10 of the 100 units. I love it. Sensor measure 1 is the same reading for the whole period. So so now we can get rid of at least one dimension. It doesn't actually tell us anything. Some of them had other peculiarities. There's lots of noise. They kind of look like this. This sensor measure 6 has me still confused. I wish I knew what it was in the physics of the world, but it basically has a baseline and occasionally it drops down. In this one, in this notebook I was like, sensor measure 6 is crap. I'm going to take it out. It isn't actually very useful. It turns out it was really useful, so I ended up putting it back in. So be careful. Things like this in time series sometimes will trick you. But what I'd say next is that I almost always, when dealing with sensor data, have to do some sort of signal processing. So in the machine learning world, we might just call it feature engineering, right? Except it's just a different type of feature engineering. So if you're not familiar with the typical signal processing or state processing things that happen in engineering, if you're going to want to get into this, I'd suggest learning a few of them. You don't have to learn them. You don't have to go to North Avenue Trade School and sit through really horrible control theory classes, but it's simple things and simple understanding will work. So this one I actually processed with a common smoother. So what common filters are, and as people that do probability, this one's actually really quite straightforward. You have some belief about the current state of the system. It evolves a step in time, so you make a prediction based on the physics of how you think it will evolve over time. That gives it a certain other predicted state with its uncertainty around it. You take a measurement of the state, so some sensor senses something about it, and but sensors have noise too, right? They have uncertainty, so you've got to deal with this uncertainty. But the nice thing is that what happens when you take two probability density functions and multiply them together, you get another probability density function that actually gives you a more certain reading. So that was kind of my hypothesis about what was going on with these jet engines is that if I knew their prior state and I knew the sensor measurement and I knew something about how they evolved, I could make a better prediction than what I was getting from the noisy data in it. So this is a common pattern kind of in dealing with these sensors for machine learning is there's some sort of processing, smoothers, interpolators. If you don't want to learn these, I mean, simple low-S smoothers will actually, regression often will work. Just try stuff, right? Be playful. So these were applied. Actually, I don't know the physics of the system. They didn't tell us that, so we don't know how it evolves. So the nice thing is you're actually able to apply the EM algorithm to try to guess all of these covariance matrices and everything that you need and try to, I say guess, but learn a good set of covariance matrices and then use that for prediction. So anyway, it comes out and you get data that's a little bit less noisy, and the ultimate result for machine learning people is that when you do the cross-validation work, you have lower error scores, right? So it kind of works out in the end. So these sorts of things need to be in your whole pipeline, right? These are what you need when you're building your pipeline. You need to put all of these smoothers, just like you would any other feature engineering thing, into your pipeline and go through all of those. So that's probably it. Do lots of different model selection. I mean, this is kind of the standard, machine learning stuff, right? Like go through your models, do good cross-validation, try different models out, be kind of playful about it. Probably the most important thing I would say, so, still when I came here to make sure there were a few takeaway points for people that haven't done this before. So this little line of code is one of the more important takeaway points. So when you're dealing with, when I've dealt with time series data and spatial data, they have a very interesting property in that they're autocorrelated. So the temperature here is, I could probably predict the temperature over there pretty well because they're spatially close to each other. And so it becomes very, very easy to kind of memorize things, and so then you get things that don't actually do good prediction on unseen data. So you got to be very careful about how you decide to do your cross-validation as you're doing your model selection. And a lot of that has to do with how you set up the data. So in time series, there's a way to see how long the autocorrelation distances are, and then basically you're just making sure that you pick stuff that's outside of those distances. Is a simple rule. There's more complex ones, but there are much simpler ones. Same with spatial distances. Or you can do what I did, which is say, look, I'm going to look at 90 of the jet engines and build a model, and I'm going to use the other 10 for prediction, right? It's not just a random split. It's take 90 and then hold out 10, which is kind of the way the competition worked, and then go through all of my cross-validation work. So that was probably that lesson learned. How am I doing on time, by the way? 2 minutes, 3 minutes? I want to make sure we get you on time. I hear there might be something out there. So anyway, that's all good stuff. Oh, I say there's a couple things I would say. One, I really like random forest for sensor data. They do really well on noisy data. They're easy as heck to tune. They work great on geospatial data often that I see because it has all kinds of noise and stuff in them. I like GBMs too because they're a little harder to tune, but they tend to do a really good job. So if you're not familiar with those, we can talk about those. 10 minutes? Oh, I'm going way too fast then. Okay, we'll go slower. Wow. Whew. Slow down. So when these, I will take a few extra minutes then. So like on this GBM model, which is what I settled on, it actually, when I was doing the cross-validation, one of the things is make sure you understand what's scoring inside of what the metric is, what you're going to be scored on, or what you're trying to do in the real world. So when you think about jet engines, the ideal situation for a jet engine is that you service it before failure, right? This occurred to me as I was flying JetBlue to Boston on Wednesday. I was like, I hope that they do this. But it turns out the scoring on this metric and that they had exactly that kind of built in. It's the way that they did it is that if you predicted early failure, predicted it earlier than it was actually happen, you had less penalty. So than if you predicted it late. Now, the prediction for them was actually a nice, smooth, differentiable function, exponential, with different exponents on each side of the 0 point or remaining useful life. I personally, flying in jet planes, would have put infinity, like a delta function, right there at the anything past 0. So keep those things in mind, work with your stakeholders, make sure you get those. So that's how we did model selection. Inside of, I will do a little bit of H2O stuff here for people that haven't seen it. So this model was built in H2O, and basically what this is doing is I'm doing a grid search with all the hyperparameters. I've settled in on GBMs have H2O GBMs have 5 hyperparameters to tune because it's distributed, so there's a couple more that are specific to the algorithm. Typical GPMs have 3 hyperparameters to tune. I've settled on, I'm just going to set the number of trees to 1,000 and just tune 2 of them, so it gets my space of search down at the risk that maybe I'm losing some opportunities, but it tends to work in practice, which is amazing. Each one of these was cross-validated. So inside of H2O, this is the flow user interface for H2O. This helps me get my 10 minutes in. So this is the scoring history on the training data as you built more and more trees on GBM. So one of the things I said is you got to be careful about GBM overfitting, and so each one of these is actually there's 10 models that were built, each 10 cross-validation models. So you can go in and take a look at each one of those models. If the website's going to work, it's not going to work for me today. Oh, there it is. Yes, perfect. So there's the cross-validation model. You can see the scoring on the validation, the MSE on the validation, is actually flat. This ended up being the best model, right? It very rarely overfit. 2 minutes. Oh, okay, great, awesome. 2 minutes now. Okay, so, wow, that was called stretching. Here's the end result of doing fairly, doing good picking your cross-validation strategy well, doing a little bit of signal processing, not having to do complicated phase space embedding, kind of doing what I consider some of the simplest things. And basically one day, which is all that I got to work on this because I have other jobs to do, was this score on the metric, which is 1,044. And it turns out there was a competition, and this would have placed between 6th and 7th place in that competition. So simple things work, right? So that's kind of the lesson. I will wrap it up. I did actually make some bullet points inside of IPython. So like I said, some sort of signal processing helps. If you're not familiar with them, try them out, experiment with them. There's a lot in SciPy. I mean, you just go play. You can figure out what these things do. Interpolation's a lot harder, it turns out. A lot of times what you've got is you've got data that comes in on different frequencies, or different spatial places, and you've got to make some decision about how you're going to line it up for machine learning. Put that decision in your pipeline, because how you make that decision matters, because you can align everything to, if you have A and B and they're aligned differently temporally, different sampling frequencies, you can align them all on A, all on B, or all on something independent and interpolate, and each one of those will give you a different result. Be very careful. Like I said, the validation strategy is important. Do just try the simplest things. And uncertainty is the name of the game when it comes to sensor data. It isn't, you get messy data all the time, but these actually come with a certain level of uncertainty that you've got to figure out how to deal with. In this notebook, didn't show some of the cool things you can do with uncertainty. A lot of times in control systems, you don't just need to know the maximum likelihood value, but the probability distribution that comes out of that, and there's some methods even inside of existing algorithms to do that. Another thing I'd say is the data is really big, so it's going to be a fun ride if you get on it. So with that, I'll conclude. So this is my last commercial. The H2O has a conference in November that has disappeared from my screen here, unfortunately. H2O World, November 9th, 10th, and 11th, and we have a special discount code for today's, for people at MLconf today. So that's really it. And you can find me on email, Twitter, and LinkedIn. and afterwards. I'll be here in the room. Thank you.